Okay, all right. Well, welcome everybody to, I think it's the penultimate physics colloquium of the quarter. Great pleasure to welcome my colleague Vikram Ravi from Caltech here to give the colloquium. Vikram grew up in Bangalore in India and was an undergraduate, I think, at ANU, and then took his PhD at Swinburne, and then I think went to Caltech as a Millikan Fellow and had a time in Harvard. You were a Clay Fellow there, was that right? And then about 3 years ago started as assistant professor at Caltech. Vikram's interests have been wide-ranging, but always, I think, rooted in radio astronomy. But he takes a very panchromatic view of the universe, as you'll shortly see. And he has been interested in what we call the transient universe, not as though it's going to disappear tomorrow, but because it's the variable part of it. And he has a strong, and has worked on gamma-ray bursts, on pulsars especially, on tidal disruption events. And what he's going to tell us about this afternoon is firstly, for the science, the fast radio bursts. He'll introduce those and explain why they're so interesting and exciting and highly plausibly useful. And then he's going to embed this in a discussion of what I regard, at least, and I'm sure he regards even more strongly, as a very exciting project that sort of represents a sort of sea change in how to do radio astronomy, which is called Deep Synoptic Array, and already there's one underway, one essentially starting in operation, and then there's a more ambitious one which he'll tell you all about. So without further ado, Vikram, the floor is yours. Thank you very much for coming to tell us about your Deep Synoptic Array and fast radio burst probes of the unseen universe.
Awesome. Yeah, thanks Roger for the introduction and also for having me here. It's always great to come up to the Bay Area. It's also great to be traveling again. I have a 6-month-old at home, and so sort of starting up a little bit now. So I'd like to tell you a bit about a combination of various aspects of my interests, both in science and in instrument building. And I'm going to tell you in particular about instruments that look like these, large arrays of very small but highly performant dishes that we believe can really revolutionize our access to the radio sky. But first of all, I wanted to say a little bit about, what is radio astronomy, right? What do we actually do with these weird-looking satellite dishes that look up at the sky? This is an image about a degree away from the galactic center, from the 2-mass survey. So this is near infrared, and you can see, all your stars. You can see pockets of high extinction caused by dust. But if you look at this with radio eyes, it looks entirely different. This is a recent image from the Meerkat telescope, and you see entirely different populations of sources. The large-scale diffuse features are sort of superimposed on some very interesting sort of filamentary structures. This thing, I encourage you to think about what sorts of animals that might remind you of. You'll be confirmed in a minute. A background of sort of more point-like things, and the sort of diffuse haze as well. And if we put some names to faces, this comprises this, almost a who's who of high-energy astrophysics. And so it might be somewhat counterintuitive to think about radio astronomers, the very low end of the electromagnetic spectrum, as probing high energies, but that is what we do at gigahertz wavelengths. This is a pulsar wind nebula. It's a very young pulsar with this sort of beautiful tail. It's a very high velocity system. These are remnants of somewhat aged supernovae. With these background sources, the little dots are individual active galactic nuclei, so active supermassive black holes outside the Milky Way. We also have this, what I've labeled as a non-thermal filament. This particular one is called the snake, and this is an example of the sorts of things that we don't know about in the radio sky. We don't necessarily know the origins of this particular filament, that little one over there, the few over there, this large one over here, and so on. The radio sky is full of both interesting phenomena that we relate with panchromatic observations to other things we know about, but also unexplained phenomena. And so, to really highlight this point, in particular to this audience, I wanted to sort of link what we observe with radio waves to, for example, directly observing high-energy particles and gamma rays. And so, really the primary gigahertz emission mechanism, so if you count up gigahertz wavelength, gigahertz frequency photons, you'll find that most of them come from sort of the emission of relativistic electrons in magnetic fields. For example, synchrotron radiation. And so if you consider an example of relating what we observe in, say, gamma rays to the radio, you'll all be familiar with, for example, the proton-proton collisions, where you have a cosmic ray proton impacting the interstellar medium, resulting in pi-meson products. Neutral pions can decay to gamma rays, which we can observe. And if you assume that you get a flux of something like 10 to the minus 3 photons per second per meter squared in gamma rays, and you sort of follow through the calculation of the synchrotron flux that you will get from the corresponding lepton products, you find fluxes, for example, of about 2.5 microjansky from the products from the decays, as well as if you have cosmic ray electrons corresponding to the protons, you end up with even brighter flux densities of a few millijansky or so. And these are eminently detectable with modern radio telescopes. Radio telescopes at these frequencies see the radio counterparts of the high energy sources observed with high energy facilities, but we also see a completely different universe because the products diffuse, we trace magnetic fields, and so on. So we're able to do this now with increasing power and access to the sky. The main drivers of these, I would argue, one, are industry-led advances in digital signal processing, as well as stream computing, for example, with graphics processing units. There's been a revolution, as we all know, in the last decade or two. We can now process gigahertz bandwidths from arrays of more than 1,000 antennas. This is not something in the distant future. This is almost being achieved now. For example, by the CHIME telescope in Canada. But the other thing which I'll say a little bit about as we go forward is that low-cost, performant receiver technology is also really now matching the performance of cryogenically cooled receivers. We're designing, for example, low-noise amplifiers that operate at room temperature with the same performance, for example, on these little antennas here from the DSA-110, as those on the very large array as well. And I'll say a bit about that as we go forward. So fast radio bursts. One of the phenomena that this new radio astronomy has enabled the discovery of are these things called fast radio bursts, or FRBs. So FRBs are much like GRBs, if you're familiar with that literature, and that these are extragalactic bursts, flashes of radio emission. We search for them in parameter spaces like these. This is frequency in megahertz, and this is time in milliseconds. And I'm going to play this forward now in real time, and this is what one would look like. You see this characteristic sweep, if I play it a bit more slowly. The sweep of the pulse to increasing delays at lower frequencies is caused by dispersion in plasma along the propagation paths. The dispersion can be related to the column density of plasma, and thus we can measure these column densities really accurately by measuring these characteristic delays of the pulses with frequency. And so, for example, if we place our burst at a redshift of 0.2 or so, and assume the critical baryon density of the universe, assume it's fully ionized, and then calculate how much dispersion we expect, that is to an order of magnitude what we typically observe. We first identified FRBs as being dispersed by much more than just from the Milky Way alone. So there are two sort of fundamental questions I'll return to through the talk. One is, what are they? There's increasing lines of evidence that link FRBs to magnetars, so highly, highly magnetized neutron stars. But nonetheless, we don't necessarily know how the population of sources that FRBs represents forms and evolves. And also the physics through which such energetic bursts, sometimes releasing around 10 to the 40 ergs, how that can be produced is not entirely known. But the other thing about which I'm particularly excited, and which refers to the unseen universe in my title, is the fact that FRB dispersions can reveal otherwise unseen baryons. So more than 80% of the luminous matter in the universe is not necessarily observed in either emission or absorption, at least at low redshifts. And we want to know, of course, how this matter is distributed, because this is the matter out of which galaxies form and evolve and impact as they evolve. And so, as you can see from this passage of an FRB through a snapshot of the illustrious TNG simulation, FRB dispersions can trace baryonic matter around and in between galaxies. This large step, in fact, this is replaying now, you'll see the step again, that is caused by a particular galaxy cluster and the intracluster medium. So just to expand on these a little bit, one, I want to say a little bit about what we know about FRB origins, and then I'll return to the baryonic physics next. A few years ago, a graduate student of mine, Chris Bohenik, who had spent most of his thesis building these tiny little receivers out of literally cake pans. We use cake pans to form the choke rings in these feeds, 6-inch pipe, bought some low noise amplifiers from a ham radio operator, and put 3 of these at 3 different sites throughout the Southwest. Along with the CHIME collaboration, we observed an FRB from within the Milky Way. And this allowed us to directly identify the source, right? Because of the Milky Way, we can follow it up. We found that it was actually coincident with a burst of X-rays from this magnetar, a soft gamma repeater. And we sort of found that its luminosity and duration were quite comparable to the population of FRBs known at the time. As we've gone forward, more instruments have filled in this parameter space of luminosity and duration, potentially suggesting a continuum between the emission of pulsars and FRBs. But nonetheless, we believe that FRB-like emission can come from magnetars that we know about. That said, when we then trace back other FRBs to positions within their host galaxies, so this is not just tracing them back to individual galaxies, I'll say more about that later, but actually positions right within the galaxies. And this can only be done with very long baseline interferometry of repeating FRB sources, of which there are only a few. What we find is a rather puzzling diversity of environments. And so just to sort of show what I mean, these are the localizations within the hosts. This is a globular cluster of M81. This is a sort of star-forming-ish region. So it's a large-ish star-forming region, but it's not particularly active in a relatively nearby Milky Way-like galaxy. And this is a rapidly star-forming dwarf galaxy and low metallicity galaxy at somewhat higher redshift. These are 3 very different environments, and yet we see these repeating FRBs from every one of them. We are puzzled by this, and so are theorists. A few years ago, I made this plot, I believe it looks slightly different now, of the number of FRBs with time, as well as the number of distinct models for their origin with time. And I found it slightly amusing to sort of try and interpret some of the structure in these curves to see how theoretical models would trace developments in the field. But the moral of the story was that at least up to about 2019 or so, we had roughly the same number of models as there were FRBs at the time. But now we have probably an order of magnitude difference as models are being refined and the population is increasing. But it's nonetheless a confusing field. I don't want to dwell on this too much, so let me move on to the next bit. Even if we don't know the precise origins of FRBs, we believe that we can use them to trace matter around and in between galaxies. And so this is, of course, a rather well-known illustration from the illustrious simulation showing the evolution of the dark matter density on the left and gas temperature on the right. And pictures like these are amazing to look at. But of course, as those of you who followed this literature will know, the illustrious simulation likely got much of this wrong. Because both the sort of flickering that you can observe if you squint, as well as these sort of large red outflows from galaxies are caused and correspond to AGN feedback models that are probably not quite what is happening in reality. And so, although this picture looks amazing and we can use FRBs to test this picture, there's actually quite a lot of wiggle room in the simulations for us to actually say something useful. And part of the reason why FRBs are a really important probe is that matter in the low redshift universe is likely what I like to think of as too hot to touch. In that, first of all, when we consider the various probes of baryons locally, we find that something like 30% or so are unobserved in either the CGM or the IGM. By observed, I mean observed neither directly observed neither emission or absorption. And this makes sense because as larger halos are formed, virial temperatures increase, and baryons typically get hotter with time. In fact, at very low redshift, you end up with baryon temperatures well over 10 to the 5 Kelvin in the IGM with a small fraction at low temperatures. And this, of course, means that most matter is also ionized. FRBs are great at tracing ionized matter, but that's not necessarily the case for every other tracer. The situation is also very complex, as illustrated in this picture of the CGM from a recent review, where we have the possibility of gas being recycled, gas being accreted in, gas outflowing, potential significant structure in the CGM of individual galaxies. Tracing such structures likely requires many sightlines through individual halos, which at some point in the future we hope to get with FRBs. Speaking of simulations, what we see here are baryon fractions as a function of halo mass, where up here we have the sort of cosmological expectation for different simulations. And the point to make here is that, one, simulations generally seem to think that less massive halos do not retain most of their baryons, but two, they disagree quite a bit as to the baryon fractions at increasing halo mass. And this is where we hope that FRBs can make an impact. So to illustrate this a bit more pictorially and really drive the message home, again, dispersion measure is a line-of-sight integral of the electron density. We expect something like milliseconds of delay per unit of dm, and we typically observe close to seconds of delay. So if we count up what we might expect to see from different components along an FRB line of sight, we of course first have the Milky Way ISM, we might have a galactic halo. The exact amount in the galactic halo is a matter of debate. We have, of course, the intergalactic medium, and we might have the host galaxy as well, both its halo and its ISM. But of course, an FRB can also impact an intervening galaxy, in which case you will get contributions from the CGM of the intervening galaxy. And in some other cases, you might pass through a galaxy cluster, in which case you'll see the intercluster medium as well. And so this is a complex situation, and of course you need to understand all these components along the sightline, for multiple sightlines, to disentangle these different contributions, and this is what we're beginning to try to do. And this, we think, is becoming a reality. So the first example where this effect was detected in FRB observations was in a recent paper that my postdoc Liam Connor and I wrote, where we basically took the CHIME FRB catalog of order of 500 FRBs, cross-correlated them with very nearby galaxies, where the sort of poor CHIME localizations of several arc minutes were nonetheless sufficient to know that we're intersecting a halo. And we found that those intersecting FRBs, typically with sort of relatively significant confidence, had a higher DM than those that were not intersecting halos. And what that told us was, one, that these excesses are real, and two, that these excesses are somewhat larger. We found a typical excess of about 90 units than expected from isolated galaxies alone. And so we appeal to galaxy groups as contributing this large amount of dispersion. So we believe we've found this effect in existing FRBs. And I'll show you another example later on where we see this in galaxy clusters as well. Now, of course, we're very excited about the future of this field. We want to find tens of thousands to hundreds of thousands to millions of FRBs, and we believe there's a lot of really fun science we can do with this. But what I want to move on to now is what we're doing at this moment with the arrays that we're building. So to realize the science, we need arc-second scale localizations of FRBs. We need to be able to not just say the FRB came from there-ish, maybe sort of there-ish, maybe even there-ish, but actually pinpoint the host galaxies of these FRBs. Because of course, to get, when you get the host galaxies, you get redshifts, and thus you can actually, measure the luminosity function. Similarly, you can characterize the host galaxies and so understand how your progenitors are linked to the stellar populations. You can probe extreme host environments. And then you absolutely need the redshifts to do the intervening baryon science, because you can characterize both the hosts as well as intervening galaxies. There's also fun things we can do with multipath propagation and Faraday rotation to probe physical conditions in these baryons. Doing this, though, is really hard, because it needs a telescope that excels along multiple axes. You need to excel in field of view to catch these things. It's about something like 10,000 or so that occur across the whole sky every day, and they last just sort of order a second when you count the dispersion. You also need to have really good time resolution, because they last for such a short time. And you need good spatial resolution to pinpoint their origins. And doing this in radio astronomy requires a radio interferometer. And so what we do is we build radio interferometers that can, in an instant, in a snapshot, localize these things to individual galaxies. This works basically by the fact that we measure the spatial coherence function of the incident radiation, and can then, from that function, using a Fourier transform relation, derive an image. This is an example where you have an image of the VLA with its 27 antennas. This is what the snapshot image would look like, and there is a very bright source right here in the center. If you work really, really hard, you can deconvolve the point spread function from this. The point spread function caused by the fact that you have this sort of shattered mirror of a telescope, not a filled aperture telescope. And then you can also find the background sources in this image. But for our purposes, we just care about the bright source in the center and its location. FRBs are typically the brightest sources in the field when they're on. So this brings me to the DSA, or the Deep Synoptic Array program. This is a ever-growing stable of radio telescopes that we're building. We started a very long time ago, before I arrived at Caltech, with DSA-1. This is Sandy Weinreb, who's been instrumental in this effort. My big part of my postdoc program was building and operating this thing called DSA-10, where I'll say a bit more about that in a bit. This discovered an FRB. Its receivers were used by my graduate student Chris Bohenek to discover the galactic FRB. This then led to DSA-110, which we're currently commissioning and completing construction of. We hope that in the future it will lead to something called TRACK, which is a dense aperture array designed to find FRBs across the whole sky, as well as DSA-2000, which will do a whole lot more than just FRBs. And I'll focus on DSA-2000 at the end of the talk. So this is sort of the sort of classic picture round in experimental sort of astronomy or physics, where we like to show pictures of building things, but there's always a story as well, which I hope is entertaining, because I never quite thought that as a postdoc I would be involved in international shipping and doing deals in various places. These antennas were bought on Alibaba.com for about 1,700 per antenna, and it was sort of a fun process to organize the shipping from the factory in China all the way to the Owens Valley Observatory in California. We assembled these like so. We designed and built these receivers. Like as I mentioned before, these are literal cake pans from a company called Fat Daddy-O's, which is heavily featured in the Food Network if you look closely. Turns out they're also a military contractor, and so they can do a whole lot more than cake pans if you ask really nicely. And so this is a very sophisticated range test of the feeds. We put out 10 antennas. That gave us a PSF that looked something like this. This is the configuration. This is what 4 of the antennas look like. And after about 6 months of operation on Sky, we were lucky enough to actually see a really bright FRB. But of course, this is here the de-dispersed profile. I've taken out the effect of dispersion to show the pulse. But if we look at this movie over here, this being the interferometer, we can also localize it and identify its position in the sky by basically fitting the point spread function to this image to figure out the origin. And it turned out to be that this tiny little telescope had seen something with a redshift of 0.66. Kind of amazing to think about photons traveling for 8 billion years before they hit these tiny little dishes. And so this led to the DSA-110. The DSA-110 is what I spend most of my time on today. It is a large array of similar dishes, but now we're, instead of having them fixed, they're moving in elevation. Instead of having just 10, we have 110. It's funded through the NSF MSIP program, and we're spreading them out as follows, with 95 in a core. We currently have about 70 odd dishes in the core, as well as 15 outrigger antennas to enable the fine localization. The DSA-110s are, it's a very large team involved, and I definitely want to acknowledge the fact that, the Owens Valley staff, as well as a large team of students and postdocs, has helped deliver this instrument during COVID. We were lucky enough to purchase all our hardware just before COVID, but then all of the construction had to happen under extreme, shall we say, circumstances on site. One example is that the low noise amplifiers were the metal casings, which were very carefully machined, were machined in a staff member's cousin's shop in Tunisia, shipped to Sandy Weinreb's house, where he then also got the transistors from this one-person company in Switzerland, took them out of the casing, walked over to someone else's house, dropped them on the doorstep. This is, of course, during lockdown period, right? And then that person had our lab and the pick-and-place equipment in his spare room, and they assembled them in-house. Went to someone else's house. The postdoc had the VNA, so we could test them in that house, then walked back to Sandy's house, who then walked over to the post office to ship them to Owens Valley. I mean, this is the sort of conditions under which this thing was built, but it works, is the short answer. We're able to deliver sort of fields of view for 10 squared degrees, time resolution of about 260 microseconds, and angular resolutions of better than 3 arc seconds. The main innovations were the sort of low-cost dish receiver package, as well as this multi-purpose digital backend, particularly using tensor cores and GPUs for acceleration. And the receivers in particular are kind of weird in that we're able to deliver LNA temperatures of sort of a few Kelvin at room temperature. A key innovation was using very, very high-speed transistors, but we're also finding physics here that is not fully understood. For example, the temperature dependence of the noise temperature around sort of ambient temperature is not something that is well understood from a theoretical standpoint, and of course working on this to better understand how we might build even lower noise amplifiers. So how does this work? Well, we stare at a patch of sky about that big with antennas that look like this. In that patch of sky, there are several, of course, galaxies, several millions of galaxies, in fact. And what we need to do is pinpoint where in this large field, which we search all the time with the coherent power of the array for FRBs, and we need to pinpoint it at this level to a location like so. This is a real FRB where we've pinpointed that is the sort of 90% confidence localization region within this sort of large face-on host galaxy. And so this is the sort of technical requirements that this thing needs to meet. And so we currently have a sample of about 30 from last year that we're working through. These are these 30 sort of ordered by their extragalactic dispersion measures. And so they start all the way from minus 22, such that the inferred extragalactic dispersion is actually lower than the Milky Way expectation. This, of course, given the secure association with the galaxy, suggests that the Milky Way expectation isn't quite right. That's fine. All the way up to nearly 1,400 units. These three are turning out to be at redshifts somewhat in excess of 1. So we're sort of working hard to understand the host environments as well as the intervening galaxy environments. So there's some reassuring things about this picture. One is that, typically speaking, galaxies in this top row look a whole lot brighter than galaxies in the bottom row. That is good, right? It tells us that there's typically more dispersion in principle, the further away you look, although there are some exceptions to the rule. In particular, like these two seem inordinately bright. The hosts seem inordinately bright for their relatively large dispersions, and especially in comparison with one sort of around them in this plot. And those are interesting as well because at least one of them we know for sure originates in a galaxy cluster at much lower redshift than suggested by the dispersion measure. So this sample, which is already growing, is allowing us to say a lot of relatively new things about FRBs themselves, because it more than doubles the yield from all other instruments combined for localized FRBs. And so as we follow up these things in their host galaxies, analyze the bursts themselves, we're able to try and relate the burst properties to the host galaxy properties and say something about both the origins of FRBs as well as the matter through which they propagate. And so I'm going to walk you through the series of 6 different things that we're saying at the moment. First, one of the first things we did was localize a repeating source, and I'm going to say almost nothing about this because all that we found was that its host galaxy was entirely uninteresting. I think there's not much more to say about that. That in itself is interesting in the context of the 3 localized repeaters I showed at the start, which were in somewhat more interesting environments than this one. Let's move right ahead to talk about the next thing, which is the one with that negative extragalactic dispersion, where what we find is that we're able to, from that, as well as a reanalysis of the expectation of the DM along the Milky Way sightline, for example, by considering nearby pulsars, as well as trying to recalibrate relations between H-alpha emission measure as well and DM towards globular clusters, we're able to talk about the contribution from the Milky Way halo and show that the Milky Way baryon content is quite sparse. And this is not just a one sightline thing. We're also considering the Magellanic Clouds as well as pulsars in the high latitude M53 globular cluster, and these all provide consistent results. This tells us, for example, that although the universe is about 16% baryons and 84% dark matter, less than 10% of the total mass of the Milky Way is baryonic. Next, these are the galaxy cluster FRBs. And so we discovered these by looking, by cross-correlating with DESI and the DESI catalog. And we found that if you plot the galaxy density in cones along these sightlines, that these FRBs lie in significant overdensities. These are massive galaxy clusters at a redshift of about 0.1. And so what's really cool is we're actually able to then measure the DM contributed by the intercluster medium of these FRBs, and we find it relatively convincing because these are way more dispersed than one would expect given the host galaxies as well as the redshifts of the host galaxies. And we're able to plot the DM from the intercluster medium as a function of impact parameter. And we're showing this with respect to 4 different clusters pulled from the illustrious TNG simulation, just to highlight the fact that 2 is nowhere near enough to really make strong statements about clusters because of the expected variation from cluster to cluster in the dispersion measure profiles. But nonetheless, we keep going, we try and do what we can, but what we really want to say is that this opens the prospect for another probe of the intercluster medium with, of course, important implications for the use of clusters for cosmology. Of course, the Sunyaev-Zeldovich effect tells you about the product of electron density and temperature. X-ray emission tells you about the emission measure, so the square of the electron density. But FRBs give you both the dispersion measure, which is the electron density column, as well as potentially the intercluster magnetic field from a combination of DM and Faraday rotation measure. In this case, we also claim in one case that, in the case that the burst is polarized, that we see a significant rotation measure excess, and we attribute that also to the intercluster medium. These are also rather interesting galaxies. So a graduate student worked with me, Kriti Sharma, was able to show that one of them in particular is a massive elliptical, which is not typically an environment where one expects to find young magnetars. And that's interesting because it says that, at least in this particular case, the magnetar likely formed from an old stellar population rather than a young stellar population. If you compare that, for example, to the distribution of specific star formation rates of different types of transients, it's really only consistent with, for example, short GRBs or, let's just leave it at that. Short GRB is the one thing that also occurs in similarly low specific star formation rate galaxies. Now, these are just 2. We can do this with a larger sample, and these, for example, show sort of non-parametric star formation histories for a slightly larger sample of galaxies, and you can see a diversity of star formation histories here, as well as, of course, some diversity in the host galaxy type. What's really interesting is that we're finding that rather than FRBs being associated with significant ongoing star formation, we're finding a somewhat broader diversity in the star formation histories of the hosts. And that tells us something interesting about how the progenitors formed. Remember that, of course, we believe these are magnetars. These didn't necessarily, we think, form in massive stellar supernovae, at least in every case. And so we're, of course, trying to measure the delay time distribution of these things. So to measure the typical sort of time since star formation that these bursts occur. And of course, the rate of transit with time can be related to the convolution of the star formation rate with time and the delay time distribution. And what we find is that although our inferred delay time distribution is steep and does favor more recent star formation, it's nonetheless consistent with a long, not just consistent, but favors a long tail to large delay times. And this is quite reminiscent of the short GRB delay time distribution, which also favors a long tail to large delay times, but also favors rather recent star formation. So we're sort of seeing that these aren't just necessarily formed in sort of supernovae that occurred very recently. We believe that at least some FRBs can be formed from a much older stellar population. Next, we're also looking at polarization. We're finding that typically we have rather high polarization fractions among FRBs as compared to pulsars. What's particularly interesting, though, is that although that statement is true for all pulsars considered together, it's not that true when you just consider young pulsars. Young pulsars typically have quite high polarization fractions, much like FRBs. Now, there are several caveats in the statement. We're talking about average polarizations among young pulsars. There isn't a rich literature on the polarization of single pulses of pulsars, and FRBs are, of course, single pulses. But nonetheless, we're starting to find a correspondence between FRBs over here and the youngest pulsars in blue over here, and these are older pulsars down there. This is linear polarization, circular polarization, and a similar correspondence is seen for circular polarization as well. We also find that FRBs, with not much confidence, but some confidence, also inhabit rather more magnetized environments than your typical pulsar in the Milky Way. But that's, I think, superseded in sheer, what's the word, coolness to look at in comparison with the actual pulse profiles, because we're seeing amazingly rich polarization structure among these bursts. This is one example where you see sort of the four Stokes parameters, Stokes I in black, Q in sort of solid blue, U in dashed blue, and V in gold. And what you see is a sort of change in the polarization position angle across these two sort of pulses from this burst, as well as a flip in the sign of Stokes V. I like to visualize this a bit more on the Poincare sphere, where you can sort of see the burst, that same burst as a function of time, inhabit two completely distinct regions, but also there appears to be, noise-like structure there as well, especially this last little loop. We have no idea how to interpret this yet, but we're beginning to first put the data together and then say a bit more. I think it's particularly interesting with respect to some of the more extreme emission models out there, and hopefully will inform others. And so, to get to the status of the DSA-110, it's in commissioning, and we expect to complete construction by this summer. It's detecting something like an FRB per week. That should go up by nearly a factor of 2 by the time we have the full array this summer, hopefully yielding our sort of 100 per year that we wanted at the very start. We expect near real-time public alerts with localizations to be sort of coming out of the array soon. And plenty of upcoming science results as well. For example, we're undertaking a significant survey of intervening galaxies to try and understand the sightlines towards a sample of several tens of our FRBs. And we're also doing a few other things with the array that we expect to be exciting in coming years. And so for the last sort of 10 minutes or so, I want to say a bit about DSA-2000. But if there are any questions on FRBs, now's the time. I can take more questions at the end as you think of them, but go ahead.
I just had a question about how do you do calibration on all these arrays, especially given the long time scale, the long observing times and the short measurement time?
Yeah, that's a great question. So let me see if I might have a little slide on that I can show. Yeah, here we go. So, right, so multiple stages. We're constantly measuring visibilities with these arrays, and so we're constantly cross-correlating all the antennas. And we're able to do a few things with that. One is when a known bright source goes overhead, we can use its known position to solve for instrumental delays, instrumental sort of complex responses of the individual antennas that are not just delays as a function of time, and do that in sort of an hourly-ish cadence. We're also able to, when we detect an FRB, take a model for the sky behind that FRB from known radio surveys, and then fit that model to the visibility data taken then, and make images like this. So this is sort of an image of the sky behind one of the FRBs, calibrated with a known model for where these points should be. And then what we do is we go back and correct fine astrometric offsets by observing the calibrators with the best positions as a function of time around the FRB. Because these things have their own astrometric errors, and so we correct for that in a fine sense. And then and then we are able to localize. And then we also check the quality mainly by seeing how well the FRB image matches the expected PSF. And that's one of the checks on the quality that we're able to do after that. So it's multiple stages, but it's mainly done using the sort of a model for the background sky. We don't need to sort of inject signals into it. The sky is enough for us. All right, let me get back to the talk, and then we'll take questions at the end. So, DSA 2000. So we've done DSA 10, we've done DSA 110. We're now hoping to do DSA 2000. As the name suggests, DSA 2000 is an array of 2,000 dishes, 2,000 5-meter radio dishes, and the key message I want to get across is that it will do a lot more than FRBs. It's not just an FRB telescope, it is a radio survey camera that can really prove a complement to the other surveys of the coming decade. The DSA 2000 will do a variety of things, as you'll see in a minute, but one of the sort of messages I want to get across, spatial resolution of about 3.3 arc seconds, but astrometric precision in localization of that divided by the signal-to-noise ratio of each source, covering the 0.72 gigahertz band, including, of course, the H1 line. We expect to use the Hot Creek Valley site in Nevada, and we expect first light in just a few years from now. We're going to start construction next year. Why are we excited about this? It's because of survey speed. And so the DSA 2000 excels in its ability to survey the sky faster than any other current or planned instrument. So this is a comparison of survey speed versus sensitivity. So you can see these sort of upcoming telescopes, DSA 2000 excels in survey speed while maintaining similar sensitivity to other instruments sort of on its time scale. The NGVLA will of course excel in sensitivity when it is built. It will be able to survey the whole sky to unprecedented depths. It'll be able to do H1, pulsars, FRBs, polarization, a whole lot of different things. The two key technologies that enable this are one, this radio camera digital backend, which I'll say a bit about, but two, the antenna and receiver package that's really an evolution of the DSA-110 package. We're not pushing much beyond DSA-110 in terms of that, but we are pushing it in the digital signal processing. And so really, we do see this with its order billion radio sources as proving a complement to the other survey instruments that cover essentially the entire remainder of the electromagnetic spectrum. And we're particularly excited about of course, what every one of these will deliver, but one thing that, especially with the cross-matching and redshifts, we believe the SphereX will prove quite useful in a sort of whole sky survey in radio source identification. Our science themes center around these three areas, which map neatly to the Astro 2020 Decadal Survey themes. We are doing a lot of multi-message astronomy, both by doing the follow-up of LIGO-detected neutron star mergers, as well as pulsar timing for gravitational wave detection. We'll conduct continuum, H1 and polarization surveys to study our cosmic history, as well as probe the dynamic radio sky on a variety of timescales. So just to expand on that, multi-message astronomy is super exciting. I don't need to sort of belabor that point. We will dedicate about 25% of our time to pulsar timing for gravitational wave detection. This will target individual sources of gravitational waves that are binary supermassive black holes. The DSA 2000, we believe, will really give us a much better chance of probing this population. By also dedicating significant time to following up the radio afterglows of neutron star mergers, we will actually be able to detect these things all the way out to the horizon of the 05 run of LIGO, as well as the within the localization regions of a future 5 detector network. With continuum surveys, we're really probing, in the most part, star formation, but also really capturing almost all the radioactive AGN out there. For example, we expect to be able to detect these rapidly star-forming galaxies at redshift 6 across the whole sky, not just in individual deep pointings, as well as probe AGN and diffuse synchrotron on a variety of scales. We are interested in the weak lensing possibilities for this array as well, because the PSF will be so well understood that we should be able to super resolve it by factors of a few at least. And we have a paper that looks at, for example, the weak lensing constraints we get in comparison with DES and other surveys as well. H1, super exciting, from the galaxy all the way out to redshift 1. For example, we expect to make images like the state of the art across the whole sky for nearby galaxies, probe cosmic structure out to very large distances. This is the DSA-2000 simulation, as well as potentially probe diffuse H1 around and in between galaxies. I'm rushing through this because I'm nearly out of time, but we also will do the sort of slow transients by doing a 16 epoch radio survey, not just one. We'll keep going back to the whole sky to catch, a whole lot of interesting cases. How does this work? The radio camera is really the key concept I want to convey here. This idea that we're not just delivering visibilities like I discussed before when it comes to radio source localization. We're delivering images. The system will not store visibilities, it will store images. We will calibrate them in real time, but then we can post-process them in the same way that we would for an optical survey, having saved the images. So the idea is that traditional radio telescopes basically produce visibilities for every baseline, and we would have 20 exabytes per year of data if we did that. That is simply not tenable. The reason why we can not do that is that we have so many antennas that instead of a sort of image of the sky with this PSF like the VLA looking like so, the same image with DSA-2000 with this PSF would look like this. So this is a simulation not just containing sort of the PSF effects, but also containing various forward model sources of noise. For example, calibration errors, errors in the primary beam model, errors in the ionosphere that we cannot model, so on and so forth. We expect images like these coming directly off the telescope. We need dynamic ranges of about 10 to the 5 in order to detect the large number of sources we want to. And so the radio camera really delivers these images that we save to disk and then process at leisure. What does this look like? Well, we've got a rather rapid timeline, shall we say. We're sort of in this preliminary design phase, which will culminate in a preliminary design review. We then will get to the final design review and construction sometime next year. We expect to be able to do that, having completed surveys on that Hot Creek Valley site by that stage as well. The total construction cost is $144 million. This is really enabled by the fact that we're using this evolution of the DSA-110 low-cost antenna receiver technology to supply these large numbers of antennas. And I want to advertise this science meeting in just a couple of weeks down in Pasadena. You can still register if you contact us, so if you're interested in coming down and hearing more about it, please let me know. And with that, I'd like to conclude. So I've talked a bit about how we're deploying these large arrays of small but performant antennas. We're able to really, with this, I think, revolutionize the way that we see the radio sky. The DSA-110 is currently detecting FRBs at the rate of about 1 per week. This was one we saw just this morning, our, I believe, third brightest one so far. And what I'm not showing here is a third, much fainter component, sort of a similar time further on. We believe that we're able to now make some statements, and we'll continue to be able to make statements as we assemble these samples of order 100 sources, that can really change the way that we see the origins of FRBs, as well as the matter through which they propagate. And the DSA-2000, we're super excited by, and we're looking forward to what it will do in the future. Thank you.
Thank you very much, Vikram, for giving us a snapshot of a lot of science. It's exciting, and as we can see, happening on a daily basis, and I think some considerable insight into what it takes to make a project work. All the sort of things that are not in textbooks, not in instruction manuals, to get something to work, particularly over COVID. So congratulations on being able to keep the schedule over a very difficult time, and every good wish for keeping to that schedule for DSA 2000. So Bob, you have a question?
Yeah, I do. I got here late, I apologize.
No.
Okay, so I'm struggling a little bit to understand what you actually measure.
Okay.
And let me just tell you, what I think I saw was in one of these bursts, a total power, one. Two, a slope, which is telling you about integrated density of the propagator. So a power, a slope, and then maybe downstream some polarization information as a function of frequency. But you didn't talk much about that.
That's right.
So except for that last, it's two numbers.
No, well, the yes and no. So yes, and that those are the two primary observables, setting aside the localization information.
I'm sorry, four numbers.
Yes, with a couple of other things. So then once we have the localization, we have the host galaxy, which gives us the redshift. That gives you a luminosity, as well as a distance, and as well as a proper timescale. We then are able to characterize the host galaxy. We're able to characterize the intervening galaxies, and so on and so forth. But yes.
Theory, okay. What you actually measure is two numbers, let's say four.
Okay.
And
maybe Vikram, you should say, just explain how long a typical FRB lasts, and what sort of time structure you have in the waveforms.
Yeah. So I think So I mean, I guess the key point is that yes, I believe that we're able to pull out a lot with just those four numbers, but these are richer bursts than just those four numbers. Right? And so I didn't talk at all about how we're really trying to use, for example, the Faraday rotation, how we're trying to interpret the polarization properties, how we're trying to interpret, for example, the change of the burst with frequency as well, interpret the shape of this burst, which we think corresponds to multipath propagation. There's a lot more information that can be gleaned that, I simply didn't mention.
Well, okay, just to follow up on the question. So it's, Roger's got his hand up, there's basically, what is it, 0.1 millisecond there.
Indeed.
Width. And I'm not immediately sure what your time resolution is, but...
the time resolution is, in this case, literally the step, which is about 32 microseconds.
So I'm a little lost about what the rest of the signal is. That's all. I'm in the audience. I'm not an expert in this subject, and I'm basically struggling to understand what's in this signal. I see something that's pervasive in the sky, very mysterious. So where the hell it comes from exactly? Okay, something that short, that infrequent. It's not that infrequent, pop, 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 going off in the sky. So it's something that happens sort of generically. Okay, but what is it? Okay. What is there any information in the signal that you're seeing that tells you what it is?
Yes. So, for example, the fact that you have a certain time scale tells you something about the length scale of the emission region. The luminosity also tells you something about the energy density of the emission region. The polarization tells you something about the emission mechanism. The frequency properties, both the bandwidth as well as the structure within it, might tell you something about microstructure in the pulse, but then also the sort of large-scale properties and frequency tell you about the material through which it propagated, that sort of thing. So there's a lot of little bits we can pull out of it. Yeah.
Made my point.
No worries. Yeah.
Thank you.
Well, maybe you should answer Bob's almost asked question, what are they?
Yes.
Every explanation out there.
I carefully avoided that, but yes.
Whatever it is, it's small.
Yeah, so I carefully avoided that, but
It's small, it's obviously it's small.
yeah.
So what's that small that emits that much power?
Yeah, so we think that, so one object was associated with a magnetar, so a neutron star with somewhat over 10 to the 14 Gauss surface field strength. In particular, we associated it with a sort of rather luminous burst from that magnetar, which we believe occurs due to some sort of rupture in the crust, beyond that, the problem with that is when you go to other galaxies, sure, we might say that they're magnetars. I would then say that if they are magnetars, they're formed through multiple channels, not just one way, in analogy to supernovae. Yes, I think that is as far as one can go. In terms of the emission mechanism itself, I think there are several models out there that, some more explanatory than others, but yes.
Roger. So for a burst that has a sort of intermediate DM, so you know it's safely extragalactic, but not very high, so you know it's relatively nearby universe, has your follow-up actually pushed the flux down to the point where you're faint enough to say something interesting on the upper limits on the counterparts?
On the prompt counterparts, you mean, or or transient counterparts?
Do you ever get below galactic scale luminosities for the host? Do you think have things out in the extragalactic environment?
I see what you're saying. So, let me go back to my little collage. Yeah, actually, let's go to. No, let's go to the collage. Yeah, I like that one. I like the background. Sorry, one sec here. Here we go. So, this one is my favorite one because that we've gone down to 26th magnitude and not seen anything. That also happens to be the brightest one. It's about 300 sigma. And so that's the one case where we really don't see a host. This is all Pan-STARRS data. These three cases, despite they're not looking like as a host, there is something at about 24th to 25th.
Do you know what 26 mag at, taking that DM as indicative
of the distance, yeah.
What luminosity does that
that's about 50th Milky Way.
The 50th of L-star.
Yeah.
Okay.
So it's not, yeah. So what we need to do is sit on it with a spectrometer and see if we can see any lines, at the very least, because sometimes if you're lucky enough. If you're lucky. Yeah.
More questions, especially from students.
Get web.
Yes, actually.
I have a question about, you said that the FRB population's part of its star formation rate is comparable to soft gamma ray bursts, but you also said that there are some other properties that were similar to young pulsars. I would think that those two statements are sort of contradictory.
Yeah.
Gamma ray bursts are
So first I'm not saying that FRBs are directly associated with short gamma ray bursts. I'm saying that the populations look similar to them. But one direct way to make them consistent is that if short gamma ray bursts are ubiquitously neutron star mergers, a good fraction of the mergers will yield magnetars. Yeah.
It might also be worth remarking that out of the hundreds of suggested explanations out there is precedent in the sort of astronomy for eventually 2 or 3 of them describing the whole class, so you don't have to be convinced there's only one explanation.
Indeed, yeah.
But there's no precedent for 100 explanations, there is a precedent for 2 or 3, as you well know. Matt, there you go.
So you mentioned briefly that you're expecting, is that exabytes or petabytes of data? Are there any plans for releasing even just a small percentage of that data to the radio diffuser as a whole?
Yeah, so let me go to my slide on, here we go. Yeah, so we're planning to undertake a variety of surveys for DSA-2000, mainly this all-sky survey, and the exabytes of data are visibility data. The image data, the total project over 5 years will yield about 50 petabytes. That is very releasable, not necessarily by email, but certainly in a store at the Observatory. But then the continuum part of it, we plan to make completely accessible in a SDSS type archive. The spectral-line part we will release, but then we'll probably release only cutouts around sort of identified sources. But then if people can access the rest, we would have to then use our servers to do that.
You said when you were looking at the baryon fraction in the Milky Way that one of those estimates came from the LMC. I'm curious how that was.
That's from pulsars in the LMC. So just like the globular cluster M53, because we know the distance of the LMC and it's off the plane, you can sort of take the minimum DM of a pulsar in the LMC and say that is an upper limit on the halo DM in that sightline. We can do the same for globular clusters. Yep.
How would you compare the DSA-2000, which is relatively dense array with pretty well localized stuff, to something like CHIME, which is going a couple outriggers are like 1,000 kilometers apart? What are the two differences between those two things?
Yeah, so CHIME, especially with the outriggers, is an FRB machine. It's designed to detect with the core and then localize with a couple of outriggers. DSA-2000 is not an FRB machine. We do FRBs on the side, but it does a lot of other things. And so it's designed to do the sort of radio surveys. It's designed to be sensitive enough for the pulsar timing while doing FRBs. It's not a purpose-built FRB machine the way the DSA-110 or CHIME with outriggers is. That said, we believe, because we have the sensitivity and a reasonable field of view, our FRB detection rate will be quite high. So at the level of CHIME with outriggers, perhaps a little more, but our localization will not be nearly as good as they will get with their outriggers.
More questions? Comments?
Dave, just broadly speaking, how would you separate out the science goals, the differing science goals of DSA-2000, NGVLA, and the SKA?
Great question. So NGVLA is very different because it's focused at higher frequencies than we are. Although they plan to have a low frequency receiver, that is not the driver. Right? So they're really targeting high redshift and at the very high frequencies on protoplanetary disks. There is also, there's many other things you could do at sort of 30 gigahertz, like they want to do galactic center pulsars. They want to do, in general, they want to be a good imaging instrument and so on. They want to do LISA source localization where the high frequencies may be worthwhile. The SKA is more similar to DSA-2000 than the NGVLA. It is designed for the same frequency range. A couple of differences. One is that it is optimized for individual fields, or maybe small fields, where you can stare for a long time. And there, in order to beat down the confusion limit, they need the higher angular resolution. And so their baselines will be out to about 200 kilometers. Our maximum baseline is 19 kilometers. Yeah, I think otherwise the SKA is putting a lot of effort into sort of subarray modes for pulsar timing and stuff like that. Because we're dedicated, we can just dedicate a lot of time to it. And so, yeah, it's more similar to the SKA. Yeah.
Okay, well,
Thank you very much indeed, Vikram, and good luck with the project.
Thank you. I should leave this here before I forget.
Excellent.
Yeah, thank you. There we go.